Good evening, ladies and gentlemen, and a warm welcome to the Vidya Jyothi Professor V.K. Samaranayake Memorial Oration 2025, organized by the University of Colombo School of Computing. This annual event is a tribute to the visionary legacy of Professor V.K. Samaranayake, whose pioneering work in the field of information and communication technology has profoundly influenced Sri Lanka and beyond. We are honored to have esteemed dignitaries, academics, students, and distinguished guests with us here today. Thank you for joining us in celebrating the life and contributions of an extraordinary individual. Ladies and gentlemen, may I kindly draw your attention to the important tradition of our event, the lighting of the oil lamp. The ceremony will now take place outside the auditorium.
To commence this evening's proceedings, we begin with lighting of the traditional oil lamp, a symbol of enlightenment and knowledge. May I kindly invite our distinguished dignitaries and special guests to light the oil lamp. I cordially invite Vice Chancellor of University of Colombo, Senior Professor H.T. Karunaratne, Acting Chairman of UGC, Senior Professor O.G. Dayaratne Bandara, Mrs. Shriya Samaranayake, Professor Frank Lyman, Director of University of Colombo School of Computing, Dr. Ajantha Athukorala, Deputy Director of University of Colombo School of Computing, Professor Kasun D. Soisa, Head of Undergraduate Studies, Dr. Chamak Kapitiagama, Dr. Johanna Barzen, Dean of Faculty of Technology, University of Colombo, Professor Ranjana Piyadasa, Senior Lecturer of University of Colombo School of Computing, Dr. Nalin Ranasinghe. Thank you. May this light guide us through an inspiring evening ahead.
To begin the ceremony, let's honor the state by rising for the national anthem.
Namo, 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 namo,
Thank you. Please be seated.
Visionary, innovator, educator. Vidya Jyothi, Professor V.K. Samaranayake, fondly remembered as the father of IT in Sri Lanka, dedicated his life to transforming a nation through technology. Born in 1939, Professor Samaranayake began his journey as a mathematician but quickly saw the potential of computing to shape the future. His efforts led to the establishment of the Department of Statistics and Computer Science at the University of Colombo in 1985, a milestone that paved the way for the creation of the University of Colombo School of Computing. Professor Samaranayake was a pioneer in introducing computer education and digital innovation to Sri Lanka. Under his leadership, key initiatives like government computerization and IT education reform became reality. He was also instrumental in setting up the Information and Communication Technology Agency, ICTA, which continues to shape the country's digital future. His vision extended beyond the present. Through his dedication, Professor Samaranayake laid the foundation for a tech-savvy generation, empowering Sri Lanka to compete on the global stage. His legacy lives on in every innovation, every institution, and every IT professional he inspired. Today, we honor his unparalleled contribution to the field of information technology and his unwavering belief in the power of knowledge. Vidya Jyothi Professor V.K. Samaranayake, a name etched in the history of computing in Sri Lanka.
Teachers lay the foundation of knowledge and education in every person's life. They not only educate us, they teach us the essence of life. University of Colombo School of Computing has been annually conducting the Vidya Jyothi Professor V.K. Samaranayake Memorial Oration since 2007. To express its gratitude and appreciation for the enormous service rendered by the late Professor V.K. Samaranayake, the founding director of the University of Colombo School of Computing, I would like to use this moment to thank, first and foremost, Vidya Jyothi Professor V.K. Samaranayake, the father of information technology in Sri Lanka, and all our lecturers, past and present, who prepare us for the world outside. Our teachers have been the epitome of strength and a great pillar of support. So please rise from your seats and join me in a 1-minute silence period to remember and extend our gratitude to all these amazing human beings.
Thank you. Please be seated. To formally welcome you all and set the tone for this evening, it is my pleasure to invite Dr. Ajantha Athukorala, Director of University of Colombo School of Computing, to deliver the welcome address.
Good evening, all. The Vice Chancellor, University of Colombo, Senior Professor H.T. Karunaratne, Professor V.K. Samaranayake, Memorial Oration orator, Professor Frank Lehman, Mr. Samaranayake, all the invited special guests, staff of University of Colombo, ladies and gentlemen. It is my great honor and privilege as the director of the University of Colombo School of Computing to welcome you all to the Professor V.K. Samaranayake Memorial Oration 2025. Today we gather to commemorate and celebrate the life of legacy of visionary leader, pioneer academic, and a national icon in the field of computing, Professor V.K. Samaranayake, known as the father of IT in Sri Lanka. Professor Samaranayake's contribution have left an indelible mark not only on the University of Colombo, but also in the entire nation. As the founder and the first director of the UCSC, Professor Samaranayake led the foundation of what has become a center of excellence in the IT education, research, and innovation. His tireless efforts introduced computing to the University of Colombo and catalyzed the integration of IT into Sri Lankan higher education system. Beyond academia, his vision and leadership were instrumental in shaping Sri Lanka's IT landscape, empowering generations to embrace technology and innovation for nation's progress. This evening, we are privileged to have with us Professor Frank Lehman from the University of Stuttgart, a globally renowned pioneer in computing, as the orator for this year's memorial lecture. Professor Lehman's remarkable contributions in the field of computing and his groundbreaking work resonate deeply with the visions and the legacy of Professor V.K. Samaranayake. This oration is not just an event, it is a testament to our enduring gratitude and respect to Professor Samaranayake's unparalleled contributions. It is a moment to reflect on his achievements, draw inspiration of his life, and continue his mission of advancing IT to the betterment of the society. I warmly welcome all your esteemed invitees who have joined us today to honor Professor Samaranayake's legacy. Your presence reflects the profound impact he had on individuals and institutions alike. Let us celebrate his legacy and may it inspire us to strive for excellence in innovation in our respective fields, as he did throughout his extraordinary career. Thank you, and I wish you all an evening filled with inspiration and reflection. Thank you.
Thank you, Dr. Ajanta Tukorala, for your warm words of welcome and for highlighting the importance of this significant event. Next, we have the honor of hearing from Senior Professor H.T. Karunaratne, Vice Chancellor of the University of Colombo. Professor Karunaratne has been a firm supporter of academic excellence and innovation at our university. Please join me in welcoming Senior Professor H.T. Karunaratne on stage.
Very good evening to all. Thank you very much. Acting Chairman of the University Grants Commission of Sri Lanka, Professor O.G. Dayaratne, two former Vice Chancellors here, Emeritus Professor Shanika Hiriburegama and Dr. Hiriburegama, and then Dr. Ajanta Atukorela, Director of the University of Colombo School of Computing. Today's orator, Professor Frank Lehman, and invited guests, all participants. It gives me great pleasure and honor to see you today that this kind of event happening in the University of Colombo. In fact, I was fortunate to work with Professor V.K. Samaranayake at the beginning of the UCSC in year 2001 as a Senate nominee to the first council here in this University of Colombo School of Computing for 3 years. Under his leadership, I learned many administrative skills and administrative methods how we followed. Anyway, that we know the University of Colombo, since there are some outsiders, let me just to say that about few words on University of Colombo. University of Colombo is started from 1870 by the first Colombo Medical College. Then in 1921, University of Ceylon. Then in 1940s, of course, University of Ceylon, Peradeniya campus and University of Colombo, Colombo campus. Then in 1978, we have the Act, and 1979, January 9th, appointed first Vice Chancellor of the University of Colombo. And now we are, of course, more than 104 years or long history we have in the university. In this regard, particularly when it comes to Faculty of Science, it has expanded more and more into different specialties, so that the computer has come from the Faculty of Science. Even I think our current director is also graduate from the Faculty of Science in the University of Colombo, and they created this marvelous and contributory place of the University of Colombo called the University of Colombo School of Computing. And they are doing excellent job for the country. And of course, we know that not only training undergraduate students, but for postgraduate and research and integrating with the community and public sector organizations and private sector organizations, they are doing excellent job in the country. So that in this regard, we know particularly Vidya Jyothi, Professor V.K. Samaranayake contributed and led to this field. And of course, it is essential to have this kind of memorial orations, because that reflect the history, and we can go back to how the institutions created, how they sacrificed, and it is not by the number of years they served in the University of Colombo, because it is not 8-hour work norms, and they have worked for all 24 hours every day, hard working by those excellent people. The University of Colombo is today because of their contribution. So therefore, I don't want to take much time, but I should thank for UCSC organizing this kind of excellent event in this evening. Thank you.
Thank you, Professor Karunaratne, for your insightful words and for emphasizing the enduring impact of Professor Samaranayake's contributions to the ICT field. Ladies and gentlemen, distinguished guests, it is now my privilege to introduce our esteemed orator for this evening. To present the introduction, I would like to invite Dr. Nalin Ranasinghe, Senior Lecturer at the University of Colombo School of Computing, on stage. Please join me in welcoming Dr. Nalin Ranasinghe.
Vice Chancellor, distinguished guests, invitees, ladies and gentlemen. I am greatly honored to present a short background of the orator, Professor Frank Lehman. Frank Lehman studied mathematics, physics, and astronomy, and received his master's degree in mathematics in 1982 and the Doctor of Philosophy in Mathematics in 1984 from the University of Bochum in Germany. Following his PhD, he moved to computing, becoming the chief software architect and distinguished engineer at IBM Research and Development. In 2004, he moved to academia, becoming full professor of computer science at the University of Stuttgart in Germany. His research interests are in software architecture, distributed systems, and quantum computing, contributing to application breakthroughs that have been highly valued by the industry worldwide. He is the co-author of a large number of peer-reviewed papers and nearly 70 patents to his credit. He is an elected member of the European Academy of Sciences and Arts, Kurt Gödel Visiting Professor of Quantum Computing at the Technical University of Vienna, Fellow of Asia Pacific AI Association, member of the Expert Council on Quantum Computing of the German government, and the recipient of many honors, and not to say the least, a technology fellow at WSO2, the very Sri Lankan global software company. With his cross-cutting background in mathematics, astronomy, and computer science, Professor Lehmann is eminently suitable to deliver the today's oration in honor of Professor V.K. Samaranayake, who himself was a mathematician, astronomer, and a computer scientist. I now request Dr. Ajanta Atukorala, Director of UCSC, to formally invite Professor Lehmann to deliver the oration by presenting him with the Professor V.K. Samaranayake Oration Medal.
Thank you. So I need to get up my, can you hear me? Okay, yeah. Did it lose connection?
No, it's take a little while.
Oh, so it takes a little while, okay. Well, it says it should be started. I think I go out. Wait a second. Start again. Choose location. This one, synchronize. Ah, here we go. So I learned that as long as I have this medal, I'm allowed to speak. So I can do it very good. So, oh. So the talk today was, I tried to combine mathematics, astronomy, and computer science. And the title is Cosmology and Data. Oh, come on. So, just a second. So, I want to see the red dot here. Ah. Otherwise, you can't see it enough. Okay, I go with the pointer. So first of all, I'm going to introduce curvature of curves, then curvature of surfaces. Then I move on and try to explain what is the meaning of curvature at all, and how to detect holes in space. And if I speak about space, I mean the cosmos, the universe. Then I give you a brief introduction, this very simple algorithm, how to determine certain kinds of holes that are important in databases. And next I introduce something in-depth mathematics, but don't be shocked, I always have tons of figures, right? And I introduce holes in data sets and how you can use holes to find out what your data basically means. And then, as usual, I do conclude. So what is a curve? A curve is a line or a circle that got somehow deformed in space, but it must not have any edges, right? So it means I do have an interval here in the real line and have different maps, and here you see several of the curves. And more precisely, you have a differentiable map, K, from the interval to the three-dimensional space, and this is a curve if and only if it is regular. That means its derivative is non-zero. Because if you have a derivative that is zero, there might be singularities, edges, and so on, and this is no good. The interpretation is you have here the interval, here, and the map is here the curve, and then you have the tangent lines here, tangents, right? And I have tangents at different points, and the curve describes, this is the interpretation, the movement of some particle. And the tangent describes the speed and direction of the particle that is moving along the curve. And very precise, the tangent is the derivative of this function k. And an indicator of curvature is the following. Here I have a curve, it is not really curved. That means it's weakly curved and direction and speed changes only a little. Here's a very different curve. And here, within a small amount of time, the direction of the tangent is really significantly changing. That means we only need to take a look at the change of the direction of the curve, but the length of the tangent, but the length of the tangent is irrelevant. Only the direction already indicates whether there is curvature or not. And the amount, the length of the tangent, which is the velocity, is irrelevant. So now do you measure it? So how do you do that? You have the tangent here, and then I basically divide the derivative, k prime, by its length, and then I get the unit vector, which represents merely the direction, and the length of the vector is irrelevant anymore. So what I do is I take k prime and take then the length of k prime and then have the tangent, right? And the amount of change of the direction then is an indicator of curvature at a certain point t, because a curve typically is curved differently at different points, right? Here's an example. I have a straight line, and the straight line, the tangent on the straight line doesn't change at all. I move along the curve, and the direction doesn't change. So our interpretation is there is no curvature. It's a straight line. And here, and I didn't compute it, if you have a circle of radius capital R, the curvature turns out to be 1 divided by R. If you have a small circle, 1 divided by R. So this is much more curved here, this small circle, than the bigger circle. And instead of taking the normal, I can also, the tangent, I can also take the normal to indicate curvature, because the normal is perpendicular to the tangent, and if the tangent moves, the normal moves this very same way. So I take a vector of length 1 that is perpendicular to the tangent. This is then the normal vector. And obviously, if the normal changes, just like the tangent, so I can use the normal too, which will become important if I go to higher dimensions. So how do I measure length? As I said before, the tangent is the derivative divided by the length of the derivative. And how do I measure the length of the derivative? Very simple. It's Euclidean. It's a Pythagoras theorem. I basically take the x-coordinate, square it, and the y-coordinate, and square it, take the square root of it, then have the length of the vector. Very simple. We learned that at school. And in mathematics, we call this a Riemannian metric, right? Abbreviated as G, G of k prime. And this G depends in astronomy, based on general relativity, on the location where I measure the length. So when I'm in space, close to high massive stars, the length is different, right, than on Earth. So the existence of mass changes length measurement, right? We will come back to that later on. So curvature depends on the type of length measure, and this metric g in space changes often with the location where I perform the measurement. So now we have a rough understanding how to measure curvature of curves, and now we move on one dimension into surfaces. So here I have a surface, it's a sphere, right? And we not only have a single tangent, but we have a whole bunch of tangents. Here's a single tangent, I have a curve k through this point P, right? And then I can basically take the tangent at point P, right? And then I can have multiple curves here. Then I get tons of tangents, and I bundle them together and get something that's a tangent plane. It's a tangent plane, right? And then I can put a normal vector on the tangent plane. So I have a whole plane, and it doesn't make sense to speak about normal on different curves, but I take a vector that is perpendicular to the whole plane, right? And then let's find out whether the change of the normal vector also indicates curvature of a surface. So here's a plane. I have a bunch of normal vectors. The plane is not curved, right? Here I have obviously curved surface, a sphere. And if I move the sphere around, the direction of the normal is basically changing. So the normal on the plane is not changing. It's not curved. That's our interpretation, what we realize. But if I move the normal around the sphere, it is changing. So it's an indication of curvature, right? Curvature kappa. Right? Change of the normal is an indication of the curvature kappa. Now we can make it a bit more formal. We define something that is called Gauss map. Carl Friedrich Gauss is the genius in mathematics, called the king of mathematicians, and he is in fear, not in fear, in reality. Here I have a surface. If we want to measure the curvature of the surface, I have some normal vectors. The normal vectors have a length 1, so I move the normal vectors to the sphere. I take their endpoints to the sphere. Here's the first point, here's the second endpoint that I basically get, here's the third endpoint, right? This is the Gauss map. The Gauss map is, so to speak, I take a point on the surface, take its normal vector perpendicular to the tangent plane, and then I move it to as an endpoint of the sphere of radius 1. And then I want to measure what is the curvature close to the surface. What I do is I take an area around the point I want to measure the curvature of, and then I use the Gauss map, right? And the Gauss map takes each normal vector close to the point P to the sphere, and then I get a different area here. Now I compare the size of the areas. So what I do is I take the volume of this n of g, right, divided by the volume of the original surface g here. And then this is an indication of curvature, right? This is bigger here. The volume here is bigger than this one. So if I divide it, this is quite curved here. And more precise, what I do is, in order to measure the curvature of a surface close to a point P, I take an area G and I shrink the area G. It's a limit process, right? I shrink it to P, and then I define something that's called the curvature of this at this point. So curvature, again, depends on the type of the length measurement, right? Curvature in place is this direction. And remember, so I'm dependent on the length measurement. Length measurement depends on the location according to general relativity. So curvature also depends where I measure the curvature in space. Now an example, again, the plane. I move the normal vectors of this G to the sphere, right? And what is the result? It's a single point, obviously. So n of G is a single point. It has no volume. If I do this division, right, I get out the curvature 0. Obviously, that's our intuition, right? Also, the plane is not curved at all. Right? The plane is not curved. This agrees with our intuition. Now, I did not perform the computation here. If I have a sphere of radius r, right, and then I map an arbitrary area via the Gauss map to the sphere of radius 1, then what I can get out of it is, again, 1 divided by r squared. So the curvature of a sphere of radius r is 1 divided by r squared, which basically means the Earth appears to us flat if we are standing around because r is so huge. Right? We think locally the Earth is flat, although it's, of course, a sphere, nearly a sphere. So this is, if I want to measure curvature, I need to do it at every point. But I only want to get a feeling, is the surface curved or not? So what do? I want to compute the total curvature of a surface. So what do we do here? Assume I have a linen and I have a ball, and I throw the linen, the sheet over the ball, then I get a strong curved part of the sheet here, and outside it is flat again. I'm now going to sum up the curvature at each and every point. That this is the total curvature. And this is basically, I take the integral over the curvature at each point, right? And this is then capital gamma of f. This is the curvature, the total curvature of a surface, right? And how do we measure total curvature? For this purpose, we need to introduce just another concept. What is a geodesic line? And the geodesic line is a straight curve on a surface, a straight curve on a surface, right? And how do you determine whether a curve is dead straight? By bearing. So you take a curve on the surface and you walk around, and then you only bear the tangent vector, and it doesn't change. It's a straight line, because straightness is always measured by bearing around these tangent vectors. So bearing especially means that light rays are straight. Light rays is that what we consider as being straight, right? This is it. So here's a straight line in plane, right? Admittedly, it's a straight line. The tangent vector doesn't change at all. You need to think 2 minutes about it. The great circle on a sphere is also straight. If I'm sitting on top of Earth and I'm on a great circle and I observe the tangent, I don't see that the tangent is changing because I'm within the Earth. But if it's not a great circle, it's a different one, then I can observe that the tangent vector is changing. So straight lines are on the circle, on the sphere, are great circles, right? So the straighted curves are those that are not curved at all for the observer within the surface, right? Mathematicians call them flatliner, flatlander, right? They live there and they think everything is flat, flatlander. So rays are straight because bearing depends on light. So here's an astronomer taking a look at a very nice star and is fascinated, and then at some point in time, the sun is between the astronomer and the star. So ignore the brightness of the sun, right? You can't see the star because the star is behind the sun. You don't see it because light is straight. That's what we all think. But now from time to time, the moon is passing in, right? It is hiding the sun, which we call a solar eclipse. Everything gets dark. And then at the sudden, the astronomer can see the star. Why the hell is this possible? Because light is not straight in Euclidean geometric meaning it is curved, it goes around the sun, right? So light rays are curved. They are not straight as we all think, because masses influence the light, and this is an indication of curvature of the overall space that we have, right? It's an indication of curvature because light goes around the sun. The sun is curving the space so that the geodesic line in space is not a straight line, but this kind of a curved line. So how do we measure total curvature? For this, we need to measure triangles of curves. So how are we doing this? I take the sphere again. I take 3 great circles that are meeting at 3 points, right? And the angle, how do we measure the angle of this geodesic triangle? Well, we take the tangents, right, at this point, on this line and this line. Then I have an angle gamma here. And now we want to compute the sum of the angles. We learn at school the sum of a triangle is 180 degrees, pi, right? This is Euclidean geometry. Is that also true on sphere? Let's see. So what we do is we move the angles, add them, and what we find out is the sum of the angles is bigger than 180 degrees. This is interesting. So the total curvature by measuring angles in geodesic triangles is an indication of this curvature. It's a very famous theorem by Gauss more than 200 years ago, the Theorema Elegantissimum. This is Latin. It says that the total curvature within the geodesic triangle is the sum of the angles minus pi, right? If the total sum is 180 degree, right, then 180, pi minus pi is 0, so a flat plane is not curved at all. So examples, assume that we have constant curvature, like for example on a sphere, then the total curvature of the surface is kappa times the volume of the surface, right? If I take a sphere of radius rho, right, then the kappa, as we saw before, the curvature at each point is 1 divided by the radius squared times the volume is 4 pi radius squared. That means if you have a sphere with large radius, its curvature is small, the curvature at each point is small, but the surface is huge, so it multiplies up to 4 pi. And if I a small radius, then the curvature at each point is high, but the area is small, and again, what's a surprise, we got out 4 pi. This is interesting, right? A huge ball has the same total curvature than a small ball. What's happening here? So every sphere has the same total curvature. The question is, the total curvature seems to be a characteristic property of the type of a surface. So what do we mean by the type of a surface? The type of a surface is that something that does not change under deformation. So here, for example, I have a sphere. I can deform it, I can stretch it, I get this cigar-like shape. I'm not allowed to tear it apart. Or I can squeeze it with a hammer, and then I get even a cube. So mathematically, the cube and the cigar is somehow the same. We are now in the era of topology. Topologists are quite crazy. Topologists are more crazy. If you have a torus, a tire, you can basically deform it a little bit, you deform it a little bit more, then you ditch it from the top. Just a second. So I still connected. Done? Everything's fine? Okay. He needs to fix it. So we are in the process of measuring curvature. We got an indication that total curvature is somehow a measure of the characteristic of a surface, and the type is everything that remains invariant when I squeeze it, stretch it, and so on. So a torus can be deformed a little bit. Here I take my finger and pinch it here, and then I get this, what looks like a cup. So it's very crazy for a topologist, right? A floating tire, for example, is the very same than a cup. You can't distinguish it. A topologist says, no, it's the very same, right? But try to build a car with a cup, right? So what is the origin of surface? Different types of surfaces are created by gluing handles to a sphere. So a sphere is something that has the genus 0, surface of type 0. If I glue a handle to a sphere, I get a torus. It's a surface of genus 1. What I can do is I glue 2 handles to the sphere, and then I get, people call it a Brezel. Why they call it a Brezel, I don't know. It's a genus of type 2, and so on. So this genus, this number, completely characterizes the kind of the surface, right? The genus. What the hell does it have to do with total curvature? It's another theorem by Gauss, moved to any kind of dimension by Bonnet, right? It says the total curvature of a surface is 4 pi times 1 minus h, and that means the total curvature determines the genus of a surface. That means if we want to understand the topological type of our universe, is it a sphere, is it a bretzel, right? Is it a cup? We need to measure the curvature in space. If we measure total curvature, we completely understand what kind of space we are living in, right? And obviously, the sphere had the genus 0, as we saw before, so the total curvature is 4 pi, independently what we said before, right? Blah, blah, and so on. So this is a bit more complicated in 10 minutes, right? As long as I have this. So how do I determine holes? I have a sphere. I take a rubber band on the surface of the sphere, and then I contract the rubber band. And I can contract it until I have a single point left, right? So if there is no hole on a surface, you can restrict the rubber band to a point. Here I take a torus. I take a rubber band, and I try to move it around to retract it to a point. I can't do it. Right? The rubber band can't be contracted to a point, this rubber band. But there's a second rubber band. Right? The second rubber band is this one. I can move it around. I can do whatever I want, but I can't contract it to a point. Right? That means here is a hole. In fact, there are 2 different kinds of holes. You cannot retract the rubber band to a point. You always remain a loop. So this is, by the way, homotopy theory. Mathematicians know that. But we need a different, more simple kind of approach to measure holes, simple kind of holes. What I have here is I have a line. So these are the endpoints. I exaggerated them here a little bit, right? And these are triangles. And what I can do is, they are specializations of what mathematicians call a simplex. And then I can basically glue the simplexes together by gluing the nodes together, the vertices together. So this is something that mathematicians call a simplicial complex, right? The composition of simplices. And what I can now do is, and this kind of simplicial complex represents a space. This gray space, for a topologist, can be retracted to this kind of figure here. So this is the underlying simplicial structure of the gray space. Right? Each space can be triangulated. I can add simplices to it until I exhaust the space. Right? And what I can now, so there's no hole in this structure in the gray space, right? In the underlying space. So let's try to find out what we can do with these graphs, with these simplicial complexes. So what I do is I now glue this green thing to this one, and now I find another space, and here in this space, the gray space has a hole. So the simplicial complex indicates a hole of the gray space. This structure has a hole. So we have a space, we triangulate the space by finding out what its underlying simplicial structure is, right? And now we observe something interesting. If I have this simplicial complex, I can remove a vertex that is only in a single simplex, remove the vertex and its adjacent lines. I do the next here. This one is the next. I remove it. This was fast. I take this one, right? I take the upper one. This one, sorry. This one, and then what remains is nothing, right? So this was a simplicial complex without a hole that doesn't indicate a hole. By this simple algorithm, by deleting vertices and its vertices that are only contained in a single simplex and its adjacent line, I find out whether there's a hole or not. Right? So let's prove it. Right? And such a structure is called alpha cyclic. Let's take this space here. Right? I take the first one away and the adjacent line, the second one and the adjacent line, next one and the adjacent line, and now I have only vertices that are contained in two nodes that are contained in two vertices. So the algorithm basically stops. Right? That means the simple algorithm we had before indicates the hole in the underlying space. Right? This is a cyclic, an alpha cyclic. There are alpha, beta, gamma cycles and so on, but they're irrelevant. So what the hell does this have to do with computer science? Now we come to databases. Here's a very simple databases, tables that only have two columns. It works with tables of any number of columns, but for simplicity, I took tables only with 2 columns. Here's the document author table, which document has been written by which author, author project table, which author is focused on which project, what kind of specialities does an author have, what kind of specialities are needed in a project, and who is the leader of a certain project. So now I want to have a query on this database. So what I want to find out is which documents have been written by authors that are led by Gauss. So I need the table that contains the document column. I need the table that contains, so I select document from this table, from DA table. I also need the project, the leader column, because this is the query clause led by Gauss, where leader gleich Gauss, so I also need this PL table. But if you know a little bit of relational algebra, that would be a Cartesian product. You need to join tables. Let's see how to join it. So what I do is, I join the DA table with the AP table on the author column, and then I need also the AP table here, AP, and I need a join clause, DA author equals AP author, so I join them along this column. Next, I take the project table, the project column, and join it with the project here, PL. I do that here, and project, this is now a well-formed SQL query. And now I want to find out all documents written by authors led by Gauss. So Gauss is here. Gauss is leading the project, the geometry project. Geometry project has the author Gauss, and Gauss has written document number 1. But I can do similar. Gauss also led the geometry project, and there is Felix Klein, who is an author of document number 2. So the result is, of the query, 2 documents, 1 and 2. Simple. But I can do different. The same query, what I can now do is, I can join the author column with this author column, the speciality column with this speciality column, project column with this project column. I get this query here, right? And if I do now the investigation, so Gauss leads the geometry project. Geometry project requires topology. Topology is author Klein, and Felix Klein wrote document number 2. And this is it. So only 2 values result. 2 queries on the same kind, 2 database specialists wrote 2 different queries with different results. Then you get an error report by your customer saying this is something wrong, your database is broken, right? Your DB2 or your Oracle is not correct. Now, what is happening here? Let's take a look. The tables are simplices, right? Because I have only 2 column tables, I have only lines. The endpoints are the attributes of the columns. I glue them together, right? The DA table, document author, so you get this simplicial complex here. Let's apply our algorithm. So what I do is, I get rid of document, I get rid of leader, and then this structure remains that can't be further reduced. According to what we learned 5 minutes ago, there is a cycle, right? The database is cyclic. This is bad. So, and the result of this cycle is that there's 2 different query paths, right? If you want to connect certain information, you want to select document where leader equals Gauss, you can go the blue way, or you can go the orange or red way here, right? 2 different paths are possible. So what does that basically mean? So 2 different SQL queries result from the different query paths. So these are the 2 different queries here. And the reason for this ambiguity is the hole in the database structure. And the result of the hole in the database structure is that there are different semantics of certain types of attributes in the database. Right? The blue thing here is this query. The red documents written by an author who worked for a project led by Gauss. Right? The red one is here. Documents written by an author who had expertise needed in project led by Gauss. If you analyze the 2 different queries here. So the problem is the author attribute. If you have a cycle, you are always 100% sure that you have overloaded the meaning of columns in your tables. And if you overload the meaning of columns in your tables, two different database people, or even the same database guy at two different days, interpret the attribute differently, write different queries, and different results come out. So what we did, for example, when I still was with IBM, we built a tool that analyzed databases, and if the tool said, no, you have overloaded semantics, the database designer needed to go back and change the database structure, as long as there is a cycle in the database, right? Author, paper, and so on. So you need to go back to the drawing board. This is not clear, must be specified separately. But you not only have semantical problems in the database, you have tons of different problems, and I only give you a second problem or second benefit of acyclic databases. Here's a database with 3 tables. I want to join all the 3 tables. And so the first tables are joined, you get a huge intermediate result, then you join it by the 3rd table, and in this example, the result is empty. So what you do is, you generate a huge intermediate result, a lot of processing power is dedicated to generating this result, and then the final join basically collapses into the empty set, right? And this purple table is not near at all. And you can prove that a database without holes has no unnecessary large intermediate results. Joins are monotone. When you join tables, the result set gets always smaller and smaller. You never produce unneeded intermediate results. And so there are books on properties of acyclic databases. So it's if you're a computer scientist, in practice, consider that. So the final, I didn't watch 15, okay. I have this coin here. So holes in data sets. We discussed already simplices. I have now more interesting, more nicer figures here, right? We have simplices, 0 simplex, 0-dimensional, 1-dimensional, a 3-dimensional simplex. It's a filled tetrahedron. I glue them together. It's a simplicial complex, that's what we discussed already, and the dimension of a simplicial complex is the dimension of the largest simplex. This is a 3-dimensional one because I have a filled tetrahedron here. So now I can build so-called chains. Assume that I have a bunch of p-dimensional simplices. We are now moving to arbitrary dimensions, right? So the fun part is over now. So, and then I can build a formal sum. I have geometric objects, simplices, triangles, tetrahedron, higher dimensional stuff, and I can multiply each of the geometric object by a number, a member of a field. To keep things simple, I take the field consisting out of 0 and 1. Right? And the addition is modulo 2. This is a p-chain, a chain of p simplices. P-chains can be added, multiplied by a scalar. That basically means these kind of crazy p-chains build a vector space. Right? This abstract things, geometric objects multiplied by numbers, form a vector space. You can compute with them. It's a vector space over this field here, right? Z2. And the p-chains, chain, C, p-dimension, S, okay. Now what is the boundary of a simplex? A simplex is spanned by, a simplex of dimension p is spanned by p plus 1 nodes. This is written in this manner. And I can compute the boundary of a simplex. This is the boundary operator here. The boundary of this p-dimensional simplex means I omit one vertex after the other. Right? If I omit one vertex, I get the simplex in 1 dimension less, right? I do it with one node after the other, so I get a p minus 1 dimensional simplex, right? This is the so-called boundary operator, right? The boundary operator of a point is 0. If I apply the boundary operator to a straight line, I get the sum of the vertices. If I have a filled triangle, the 2 simplex, I get the boundary. This is why it's called the boundary operator. And if I have a filled tetrahedron, right, I get only the 4 triangles that build the surface of the filled tetrahedron. Right? And this is then the boundary map. If I have a chain basically is this formal sum. I can apply the boundary operator to its geometric object here. I take the boundary of this one. And then it turns out that this operator is a linear function, a linear map. Right? It takes p-dimensional simplices to p minus 1 dimensional simplices. so-called the boundary map. And this boundary map has a very important property. If I take the boundary of this filled triangle, right, I need to leave out the C first, so I get AB. Then I need to leave out the B, I get AC. Then I leave out the A, I get BC. This is a formal sum, right? So I get exactly that, what we think what the boundary of this filled triangle basically are. Next, I apply the boundary operator to this one-dimensional beast here, right? So the boundary operator of this one basically means I leave out the B, I get the A, I leave out the A, I get the B, and so on. I get this thing. I can now rearrange it. It's a field. I rearrange it. I write this one. And now, because we are in Z2, 1 plus 1 is 0, modulo 2. 1 plus 1 is 0. So what I get out is, if you have a boundary operator, you map a chain to a lower dimensional chain, you apply a boundary operator again, you always get 0. Right? So this is in shorthand notation, right? Which basically means you have this kind of a chain. Mathematicians speak about an exact sequence, right? Because after p minus 1, you get p minus 3, and so on, right? You get a long sequence here. Boundary is 0. That means because this is valid, the boundary p minus 1, so if I first apply this boundary operator and then the lower dimensional boundary operator, the image of boundary p is in the kernel of boundary p minus 1, because in linear algebra you have learned that the kernel of a linear map is all vectors that are mapped to 0. Right? It means the image of this operator is in the kernel of this operator, which basically means, let's speed up just a second, which basically means that so here you have these two cycles. So if you have a chain that has a vanishing boundary, a chain without a boundary is called a cycle. And we will see that these are two cycles here, because if I apply the boundary operator to them, you get 0 out of it, as we saw before. So if you call two cycles homologous, right, if they are the boundary of another chain. They are homologous if they are the boundary of another chain. I'm now skipping a few lines because what is written here is only basically saying because the image is always going to the next. You can build this kind of quotient. You can divide this subvector space by this vector space. So you have here a simplex, right? A simplex, and if I apply the boundary operator to this simplex phi, I get these two cycles, the orange one and the purple one, and they are called homologous because these cycles split the boundary of something that is one-dimensional higher, homologous. That basically means that this space, this is the triangulation of this space. This is a simplicial complex that maps this space. And if I take the boundary here, I get the orange one and the purple one. And if I apply the boundary operator, I get this thing here. And now I can shrink the orange line to the pink line. And I see again, there is a hole inside. If I find homologous cycles, right, then they indicate a hole. So homolike and so on. And forget this thing and this quotient vector space. So the kernel is divided by the image because the image is always in the kernel. You get a vector space that is traditionally called HP. And this is called, the dimension of this vector space is called the Betti number. Betti is also an Italian mathematician. And the quotient is called homology group. For the mathematician amongst you, homology group, because often the vector space structure is irrelevant, homology group. And the Betti number, the P's Betti number indicates the number of P plus one-dimensional holes. Here are the holes again, where beta 0 means the number of connected components. Examples. The sphere is connected. It has the Betti number 0 equals 1. We saw before it has no two-dimensional hole because each rubber band can be contracted to a single point, but it has a three-dimensional hole. The void inside of the sphere is a higher dimensional hole. If we take the torus, it is connected. It has two-dimensional hole, namely the purple line and the yellow line. We saw it before. And it has a void inside. It has one three-dimensional hole, the air that you breathe into a tire. We saw this thing before. This is a space that is connected. Betty 0 is 1. It has a hole. Betty 1 is 1. Because it's two-dimensional, it doesn't have any void inside. The second Betty number is 0. And now the very, very deep theorem from algebraic topology that the tuple of all Betty numbers of a space is characterizing the space itself. All spaces have the same Betty numbers are undistinguishable under deformation. Right? What the hell does this have to do again with databases and data sets? Well, if I have a data point, I can draw a circle of radius r around a ball of radius r around it. This is the ball. So, and if I have 3 data sets and I have these balls around of the same radius around them, they are still disconnected. If I enlarge the radius of the lower one, the balls are intersecting, and if they're intersecting, I draw a line between them. Right? If I increase the radius even further, this line still remains here. This is this one. And because these two are now intersecting, I need to add this line here. So this is the mechanism. And if I increase the radius even further, then all 3 lines intersect. Here's still a mark. And then I get a simplicial complex of 2 dimensions. So it's not filled. If I increase further what I'm not doing here, then this void goes away, and then I have a filled triangle here. So we have a mechanism of turning arbitrary data sets that fit into some vector space into simplicial complexes. Right? So what I'm doing here's a data set, right? Any kind of data. I have drawn this kind of configuration, and I get this simplicial complex out of it. There are 2 connected components, this thing and this thing. There is no 2-dimensional hole. Everything is filled. No 3-dimensional hole, because here the tetrahedron is filled. These are the Betty numbers. They are characterizing the data set. Now I can do that continuously. I compute something that is called the barcode. So I have 3 data points, A, B, C. I draw balls of radius R1 around it, and the simplices are disjoint. I have the simplex A, B, and C. If I increase the radius continuously, I, at some point in time, arrive at this thing, then B and C are no longer connected, but they indicate that there is a simplex BC in the data set. But A is still isolated, so here its lifetime goes on. Next, I'll go further. Even A is no longer isolated, and A and B is connected. I have AB plus BC. So here the lifeline, so to speak, indicates I'm now here. I continue this. If I blew up the circles more, right, I get here A plus B plus C and so on. And note that this is here the beta 0 band. I only count connected components because there are no holes. But here at the beta 1 band, I have a hole here inside, right? This here's a hole. I'm now in the Betty 1 lane here. And then if I continue, right, then the hole is gone because we know that there is no hole, it's now filled, right? I'm back here in this simplex. Right, so this is how I can this is, by the way, the birth of the simplex BC at this radius, right? If I continuously increase the radiuses, I arrive here, this simplex appears, and after some point in time, after increasing the radius, this is here the death of the simplex BC. This can be applied to OCR, right? So you can take this characters, handwritten characters, compute, as I said before, the parse out of it, and then you can, with 100% security, find out what the characters basically are. Very interesting. And now the next thing is something called the persistence diagram. So we defined what the birth of a simplex is, what the death of a simplex is, and birth and death are now determining a point in two-dimensional space. And this diagram consisting of birth and death point is called the persistence diagram. And because birth is always less than death, typically, right, they are all above the angular bisector. So here's the barcode, and I can turn the barcode into a persistence diagram. And persistence diagram now measures how long are the bars in the barcodes. So a long line indicates a persistent simplex. It persists, right? If it's only small, it's not really persistent, right? It appears only for a short period of time. And these points are very close to the bisector here. That means points close to the angle bisector are somehow noise in your data, right? But points that are far away, they represent characteristic property of your data set, right? Barcodes and persistent diagram are, so to speak, fingerprints of data sets. They represent the abstract feature of a data set, and the points that are close before are noise. It has tons of applications, these persistent diagrams. I only brought with me a classification mechanism for transparent materials. So in chemistry, people characterize if you have a new material, you want to find out which kind of material that is, you compute the persistence diagram, and then the handbooks of these kind of diagrams where you can find out what kind of material you have at hand, right? So I conclude. Total curvature determines the type of space. That means the holes and handles that you have if you have two-dimensional surfaces. And the type of space can be determined by measuring length and angles. The Betti numbers that we introduced some 15 minutes ago characterize a space, holes in higher dimension, not only 2- and 3-dimensional. The algorithms to compute the Betti numbers are exponential, by the way, classically, but they are polynomial in quantum. So you heard that I'm also working in quantum computing. They are polynomial algorithm. This is why this research area has an explosion, because you can characterize data sets with it. Databases have been introduced here in the talk as simplicial complexes. You can determine holes in databases which indicate problems. We discussed semantical problems and a single operational property, namely monotone joins. And data sets can be analyzed also as simplicial complex. So the barcodes are used for classification, feature engineering, and so on. There are textbooks what you can do with that one. But the real summary is, right, that mathematics is very useful and extremely nice, right? So that's basically it. So thank you very much for listening. Are we taking questions? Yeah, so we are taking questions. How do we do it? If there are no questions, there's one in the back.
Sir, you mentioned quantum computing.
Yeah.
So in quantum computing, what I have heard is that it's not bits but qubits that are used. So they are probabilistic.
Say it again, they are easy or not easy?
They are probabilistic. Not qubits, you can't say whether it's 1 or 0. It can be either 1 or either 0.
Probabilistic, yes, they are probabilistic. This is why you run an algorithm thousands of times.
Yes.
Then you get a probability distribution out of it. And you need to interpret the probability distribution in order to get the real result.
So do you use fuzzy logic or any other logic to
You
control
need to
that?
I can't hear it now. Am I using what?
Are we using, do you use fuzzy logic? Do you use fuzzy logic or any other logic too?
No, it's purely statistic, no fuzzy logic. If you want to learn it, Johan and I are giving a tutorial tomorrow at 1 o'clock at this hall for 4 hours, an introduction to quantum computing. And I would appreciate if you find the time to come.
Thank you very much.
Was it yes or was it? Any further questions? Here we have a question here. What the mass is? Yeah, tangents, yes. Yes. This is why I said curves are regular. They don't have a zero derivative, because then I can't normalize it. So if a curve has, if it's a differential manifold, and if it has an edge or a cusp, it's no longer differential. Everything gets enormous complicated, right? You are in a completely different theory, which we left out here.
Why I asked that question is because in two-dimensional spaces,
Yeah.
where the derivative is zero infers a very powerful realistic concept called the optimality.
Absolutely. So I absolutely do agree, and my PhD was in manifolds with singularities because they are so important. But the curvature stuff doesn't apply here. You have to have completely different heavyweight machinery in order to define what kind of curvature you have. You're absolutely right. So it is interesting, is important. Space has a lot of singularities, black holes, right? They have a singularity curvature, the duration of the Riemann metric is zero, and so on. They are important, but it would be much more too complicated to introduce it here. Correct. Further question? I don't see any further question. Thank you for staying here for so long, right? Bearing a lot of mathematics, and I was absolutely happy to have been invited here and giving the word. Thank you so much. Thank you.
Thank you, Professor Lyman, for that inspiring and enlightening narration. Your insights on the interplay between cosmology and data have left us with so much to reflect upon. And with that, we are coming to the end of this significant event. To bring this memorable evening to a close, I invite Professor Kasun D. Soisa, Deputy Director of University of Colombo School of Computing, to deliver the vote of thanks.
Acting Chairman of UCGC, Vice Chancellor, Professor H.D. Karunaratne, Director UCSC, and all distinguished guests. As we conclude the Vidya Jyothi Professor V.K. Samaranayake Memorial Oration 2025, it is my privilege to express on heartfelt gratitudes to everyone who contributed to success of this memorial event. First and foremost, we extend our deepest appreciation to our distinguished speaker, Professor Frank Lyman, for delivering an insightful and inspiring oration on cosmology, obviously maths and data. Your expertise and perspectives have enlightened us and honored the legacy of Professor V.K. Samaranayake in most meaningful way. We wish to extend our sincere thanks to WSO2 for partnering with us to organize this event, showcasing the power of collaboration. We also wish to extend our sincere thanks to Mrs. Samaranayake for joining us today. Her support in establishing the Professor Samaranayake Endowment Fund and providing financial assistance for organizing this event is deeply appreciated. A special note of thanks goes to the staff of University of Colombo, UCSC, University of Colombo School of Computing. Your support were instrumental in ensuring the success of this oration. Lastly, to everyone who joined us today, thank for your time, interest, and participation. Your presence highlighted the impact of Professor Samaranayaka's contribution to computing and broader the academic community. Once again, thank you for all, and I wish you a pleasant evening. Thank you.
Thank you, Professor Kasandi Zoiza, for your kind words of gratitude and for acknowledging all those who made this event possible. Ladies and gentlemen, this concludes the formal proceedings of the evening. You are now invited to the reception on the 5th floor, where we can continue our conversations in a more relaxed setting. Thank you once again for your presence and for making this event a success. Have a pleasant evening ahead.